Inside silicon, the technology behind everything.
Okay, let's dive right in. If you've spent any time online lately, you've probably been hit with a tidal wave of terms. AI, machine learning, deep learning, generative AI. They're everywhere, right? But what do they actually mean? And more importantly, how do they all connect? Well, we're going to cut through all that noise and get some real clarity.
So this is the big question, right, isn't it? Are these all just fancy buzzwords for the same thing? Or is there a relationship here? Do they build on each other? Well, let's actually map it out.
And this diagram right here, this is going to be our guide. Honestly, the best way to think about this whole thing is like a set of those Russian nesting dolls. We're going to start with the biggest, outermost doll and work our way right down to the very center. So, our journey begins with the biggest idea of them all, the one that really kicked this whole thing off, the AI universe. Looking at our map, we're starting with that biggest, outermost layer, artificial intelligence, or just AI. This is the huge, all-encompassing field. Everything else we're about to discuss fits snugly right inside this circle. And here's the key thing to remember about AI. It's not a single piece of tech. It's the grand, overarching dream. It's that classic sci-fi idea of building machines that can think, reason, and learn like we do to help us get stuff done.
Okay, so if AI is the big dream, how do we actually make that dream a reality? Well, let's peel back the first layer of our nesting doll and see what's inside. And there it is, machine learning, or ML. Now notice, it's not sitting next to AI, it's a massive field within AI. You could say it's one of the most powerful ways we actually go about achieving that big goal of artificial intelligence. So what exactly is machine learning? Well, instead of a programmer writing out explicit step-by-step rules for every possible scenario, we basically just feed the machine a ton of data and let it figure out the patterns on its own. It's how your email filters out spam or how your favorite streaming service just knows what movie you want to watch next. It's really the engine that makes so much of modern AI go. So we've got the big goal, AI, and we have a powerful engine, machine learning, to get us there. But what happens when we want to kind of supercharge that engine? Let's zoom in one level deeper. And now we've arrived at deep learning, or DL. And again, look at the structure here. It's a subset of machine learning. So this isn't some totally different thing. It's a more advanced, more powerful, specialized type of machine learning. This is where things get really wild. Deep learning uses these complex structures called neural networks, which are actually inspired by the human brain. The deep part just means there are many, many layers in these networks. By feeding just massive amounts of data through all these layers, it can learn incredibly complex patterns. We're talking about the tech that lets a self-driving car tell the difference between a person and a fire hydrant, or what lets you unlock your phone with your face. Okay, we've done it. We've made it to the very center of our map. This is the technology that has completely exploded into the mainstream and is really driving the conversation today. And right there, at the very heart of it all, is generative AI. And as you can see, it's a specific application of deep learning. It takes all that power from those deep neural networks and uses it for a really special purpose, not just to understand or categorize information, but to actually create something new. So what can it create? Well, this slide shows it all. It can generate brand new music and audio. It can write computer code for you. It can create unbelievable images and art from just a simple text prompt. And of course, it can write emails, stories, and even have a full-blown conversation. It's pretty amazing. All right, we've journeyed from the outside all the way into the core. Now, just to make sure this all really sinks in, let's pull back and look at the entire structure one last time. It really just boils down to these 4 simple steps. Artificial intelligence is the whole field, the big goal. Machine learning is a primary way we try to achieve AI. Deep learning is a really powerful advanced technique within machine learning. And finally, generative AI is a specific use of deep learning that can create brand new stuff. See? Each step is just nested right inside the last. So here we are, back where we started. But now, this map, it makes perfect sense, right? What was once just a confusing jumble of buzzwords is now a really clear, logical structure. So next time you hear about generative AI, you'll know, that's a type of deep learning, which is a kind of machine learning, which is all part of the big world of artificial intelligence. And that leaves us with this one last huge question. For decades, the main goal of AI was just to understand the world. But now, we've unlocked its ability to add to the world, to create. So the real question isn't just what is AI anymore? It's become, what will we choose to create with it?
Inside silicon, the technology behind everything.
You know, we hear about AI models and algorithms all the time, but today we're going to go a little deeper, literally inside the silicon, to see the physical reality of how these incredible systems are actually built. Let's jump in. When you use AI, right, whether you're generating an image or asking some super complex question, it really does feel like magic. It's this abstract kind of mystical thing that seems to just work. But here's the thing. The truth is, every single AI system is a product of some serious engineering. It is built layer by painstaking layer on a very real foundation of silicon, math, and frankly, some very real physical limits. Okay, so to really understand today's AI, we've got to go back to the beginning, back to the very first big shift in how we even thought about building intelligent machines. So the original idea was pretty straightforward. If we can just write down enough rules, can we make a machine act smart? Think about those early chess computers. Experts would literally program thousands of if-then statements. If my opponent moves their pawn here, then I should consider these 3 countermoves. It was powerful for sure, but it had one massive glaring limitation. It couldn't learn anything new on its own. It only knew what it was explicitly told. And this led to a fundamental paradigm shift, a total flip in thinking. We stopped programming explicit rules, and we started programming learning algorithms. So instead of telling the computer how to solve a problem, we just gave it a ton of data and let it figure out the patterns for itself. That, right there, is the core of what we now call machine learning. But as our models got smarter and our data sets just got bigger and bigger, we slammed into a wall, a computational wall. And breaking through it was going to require nothing less than a full-blown revolution in computer hardware. This is what led to the rise of deep learning. And you can really just think of it as machine learning on steroids. It uses these things called artificial neural networks with dozens, hundreds, sometimes even thousands of layers to find unbelievably subtle and complex patterns in the mountains of data the internet was starting to create. Now, the breakthrough wasn't just one single thing. It was a perfect storm. We suddenly had 3 key ingredients all at the same time. 1, massive data sets from the web. 2, the parallel processing power of GPUs, which, and this is kind of funny, were originally designed for video games. And 3, new algorithms that finally made it practical to actually train these giant neural networks. And that was the moment. From this point on, progress in artificial intelligence became fundamentally tied to progress in silicon chip technology. They were inseparable. You just couldn't advance one without advancing the other. All of a sudden, the demands on chips completely changed. AI didn't just need faster processors. It needed massive parallel computing. It needed incredibly high memory bandwidth to feed all that data to the models. And because these models use so much energy, it desperately needed power-efficient designs. This is what drove the creation of all these specialized chips, like GPUs and TPUs that we hear about today. So how did this hardware revolution actually turn into the tools we use every day? Well, it unlocked the very AI that is changing our world. And let's start with the big one, large language models, or LLMs. But before we can really get how an LLM works, we need to know its basic building block. And that's the token. It's how the model sees language. Now, a token isn't always a full word. It can be a piece of a word like engineer and ing, or it could just be a single piece of punctuation. And here's the wild part. When you boil it all down, the core task of a multi-billion-dollar data center-sized large language model is deceptively simple. Predict the next token. That's it. All the incredible things we see, writing code, summarizing articles, having conversations, are just emergent properties of doing that one simple task at an unbelievable mind-boggling scale. And achieving that scale, well, that is only possible because of some incredibly specific hardware. We're talking about the most advanced manufacturing processes out there, shrinking transistors down to 5 nanometers and even smaller. It requires something called high bandwidth memory, which is kind of like stacking memory chips vertically to create a super fast data highway to the processor. And it relies on these complex chiplet designs, where smaller specialized chips are combined into one super powerful package. These aren't just nice to haves, they are absolute, non negotiable requirements.
Then, of course, came generative AI, which took all these same principles way beyond just text. Creating new images, audio, and video is even more computationally expensive. It puts enormous stress not just on the chips themselves, but on the entire physical system. The power delivery networks and the cooling systems needed to literally stop the data center from melting down.
And now we're starting to see the next evolution, agentic AI. And this is a huge shift. We're moving from models that just give you one response to systems that can actually plan, make decisions, and use tools to execute complex, multi-step tasks. So think of an AI that doesn't just write an email for you, but can also check your calendar, book the meeting, and send out all the invitations. Okay, so let's zoom out and put all these pieces together. AI isn't just some clever algorithm floating around in the cloud. It's a complete technology stack, a system of interlocking, totally interdependent layers. It all starts at the very bottom with the physical reality of advanced silicon manufacturing. On top of that, we build the hardware accelerators, like the GPUs. Then come the software frameworks that let us use that hardware efficiently. Above that are the learning models themselves, the LLMs, which are trained by specific algorithms. And finally, right at the very top is us, the human interface, how we talk to it all through things like prompt engineering. And this right here, this might be the single most important takeaway from all of this. Every single layer you see here constrains the layers above and below it. The physical memory bandwidth limits how big your AI model can possibly be. The power limits of a data center directly shape the architecture of the chips inside it. It's a fully connected, codependent system from top to bottom. So what's the conclusion here? Well, it's a profound one. Far from making engineers obsolete, AI is creating an explosion in the demand for engineering. We need more innovation across every single part of that stack, from the software and algorithms all the way down to the manufacturing floor. Which leaves us with a final thought to chew on. As we look to the future, what's going to matter more? What's going to be the bigger bottleneck and the bigger driver of progress? Will it be the cleverness of our next algorithm or the physical perfection of the silicon it runs on? The truth is, you can't have one without the other.
Inside silicon, the technology behind everything.